Hi guys, in this video we will finish off 2018's Paper 1 Chemistry. So, question 6. A student investigated the electrolysis of different substances. Explain why electrolysis would not take place in the apparatus shown. Well, because the electrolyte is a solid, ions aren't free to move and so they can't conduct electricity. 6.2. Explain why graphite conducts electricity. Answer in terms of structure and bonding in graphite. So each carbon atom makes 3 covalent bonds, which leaves out 1 delocalized electron, which is free to move around the structure. This moving electron can carry charge throughout graphite and therefore it can conduct electricity. The student investigated how the volume of gases produced changes with time in the electrolysis of sodium chloride solution. 6.3. The student made an error in selecting the apparatus for the investigation. How should the apparatus be changed? Well, in the practical, we need to measure the volume of gas produced, and here there's no way of measuring the volume. Test tubes don't have a scale, so we can say to use measuring cylinders instead, because they have a scale in which you can read off. Another student used the correct apparatus. This student measured the volumes of gases collected every minute for 20 minutes. 6.4. Describe the trends shown in the results. Looking at the hydrogen line, the volume of gas produced is directly proportional to time that has passed. However, with chlorine, the rate increases up to 8 minutes, and then just like hydrogen, it's directly proportional. So we can say that for hydrogen, it's directly proportional all the way around. And for chlorine, the rate at which gas is produced increases up to 8 minutes, and then it's steady all the way along. Therefore, after 8 minutes, the rate at which gas is produced is the same for both hydrogen and chlorine. 6.5. The number of moles of each gas produced at the electrodes is the same. No gas escapes from the apparatus. Suggest one reason for the difference in volume of each gas collected. If you remember back to the diagram, we can see that sodium chloride solution is used as the electrolyte. Therefore, the chlorine produced, it may possibly have redissolved back into the solution. So that's a possible reason it could have happened. 6.6. Calculate the amount in moles of chlorine collected after 20 minutes. Use figure 8. The volume of 1 mole of any gas at room temperature and pressure is 24 decimeters cubed. Give your answer in standard form. Reading off the graph, 6.6 centimeters cubed of chlorine is produced. We also know that 1000 centimeters cubed make up 1 decimeter cubed, and as stated in the question, 24 decimeters cubed is 1 mole. Therefore, we can also say that 24 decimeters cubed is also equal to 24,000 centimeters cubed. So if 24,000 centimeters cubed is 1 mole, and we have 6.6 centimeters cubed, to find how many moles that is, we can divide by 24,000 and then times by 6.6, or we can simply just multiply by the fraction 6.6 over 24,000. And finally, put your answer into standard form. You should have 2.75 times 10 to the minus 4 moles. Question 7 is about group 7 elements. Chlorine is more reactive than iodine. Name the products formed when chlorine solution reacts with potassium iodide solution. Well, chlorine is more reactive than iodine, so chlorine would take the place of iodine. Therefore, we would have potassium chloride, and iodine would be left out. 7.2. Explain why chlorine is more reactive than iodine. Well, chlorine has less shells than iodine. Its outer shell electrons are therefore closer to the nucleus than iodine. This means a greater force of attraction is felt by the outer shell. Therefore, chlorine can gain an electron easier than iodine. And that's why it's more reactive, because it can form an ion easier than iodine, and so it can react easier. 7.3. Chlorine reacts with hydrogen to form hydrogen chloride. Explain why hydrogen chloride is a gas at room temperature. Answer in terms of structure and bonding. Well, hydrogen chloride is a simple molecular compound because it only has the atoms of hydrogen and chlorine. Now, because they have small molecules and in general it's a smaller structure, they must have weak intermolecular bonds, and therefore not much energy is needed to break those bonds, and that's why they are a gas at room temperature. 7.4. Bromine reacts with methane in sunlight. Figure 9 shows the displayed formula for the reaction of bromine with methane. Table 3 shows the bond energies of the overall reaction. Calculate the bond energy X for the C to Br bond. Use figure 9 and table 3. So on the left hand side, the reactant, we can see we have 4 lots of the CH bond and 1 Br to Br bond. So the CH bond is 412 and we have 4 of those. So we do 412 times 4 and we add it on to 1 Br to Br, which is 193. So once you added those, you should get 1841 for the reactant side. So that much energy is needed to break the reactant bonds. In the same way, on the right hand side, we have 412 times 3 plus 366. And we are missing the Cr to Br bond, which we can just leave out for now. So we just included 3 CH bonds and 1 Br to H bond. We're going to ignore C to Br for now because we're going to find it out. So in the reactant side, to break the reactant bonds, we needed 1841 kilojoules of energy. And on the product side, the energy given out due to the products being formed is 1602 kilojoules. Now because the products are formed, energy is actually given out, and that's an exothermic reaction if energy is given out to the surroundings. So this number 1602, it's actually negative. So we have positive 1841 and negative 1602. And if we put those two together, we have 1841 minus 1602, which gives us an overall energy change of positive 239. However, in the table, it tells us we should have an overall energy change of minus 51. So what's the difference between positive 239 and minus 51? Well, the difference is 290. So the C to Br bond that we missed out must be 290. Question 8. Titanium is a transition metal. Titanium is extracted from titanium dioxide in a 2-stage industrial process. 8.1. Suggest one hazard associated with stage 1. Well, looking at stage 1, we instantly see the carbon monoxide at the end, and that is obviously a toxic gas, so we can mention that. 8.2. Water must be kept away from the reaction in stage 2. Give one reason why it would be hazardous if water came into contact with sodium. Sodium is a very reactive metal, and so when you would react it with water, it would fizz and it would produce a gas, and that gas is hydrogen. And the problem with hydrogen is that when produced, it's actually explosive and flammable. It's quite hard to store, and that's why hydrogen is often a hazard in most industrial processes. 8.3. Suggest why the reaction in stage 2 is carried out in an atmosphere of argon and not in air. Well, a main part of air is oxygen, and titanium is a metal and it corrodes and it can react with oxygen to form titanium oxide, and that is not really what we want. We want titanium. However, argon is unreactive, and so it wouldn't really react with titanium. 8.4. Titanium chloride is a liquid at room temperature. Explain why you would not expect titanium chloride to be a liquid at room temperature. Titanium chloride is a metal and a non-metal bonded together, so it's an ionic compound, and as we know, ionic compounds normally have quite a high melting and boiling point, just like salt being sodium chloride, and therefore it must mean they are a solid at room temperature. However, in this case, titanium chloride is a liquid at room temperature, and so we need to consider why it could be a liquid at room temperature, and it could be because it has weak intermolecular bonds, because titanium chloride is made up of smaller molecules. 8.5. In stage 2, sodium displaces titanium from titanium chloride. Sodium atoms are oxidized to sodium ions in this reaction. Why is this an oxidation reaction? Sodium takes the place of titanium in titanium chloride so that titanium can be extracted. And the way sodium does this is by losing electrons, and that way space is made for chlorine to bond with sodium, and so titanium is extracted. Regardless, in principle, the definition of oxidation is to lose electrons or to gain oxygen. So simply sodium loses electrons. 8.6. Complete the half equation for this oxidation reaction. Well, sodium loses an electron, so an electron is given off, and because an electron is given off and it's a negative charge given off, we're left with a positive charged ion of sodium. 8.7. In stage 2, 40 kilograms of titanium chloride was added to 20 kilograms of sodium. Relative atomic masses are those. Explain why titanium chloride is the limiting reactant. Firstly, I would write down the equations I would need. So moles is equal to mass over mR, and moles is also equal to concentration multiplied by the volume. Next, we need to convert the kilograms into grams. Next, we need to find the moles of each substance. So we have 40,000 grams of titanium chloride, and the relative atomic mass of titanium chloride is 190. And now we put these two numbers in the equation, and so we have 210.526 moles of titanium chloride. In the same way, for sodium, we have a relative mass of 92 because we have 4 lots of 23, and the mass of the sodium is 20,000 grams. 20,000 over 92 is 217 moles, and we can see here that the substance with less moles is titanium chloride, which only has 210 moles, and therefore titanium chloride will run out first because it has less moles, and we need 217 moles of titanium chloride to react with 217 moles of sodium. 8.8. For a stage 2 reaction, the percentage yield was 92.3%. The theoretical maximum mass of titanium produced in this batch was 13.5 kilograms. Calculate the actual mass of titanium produced. The equation for percentage yield is the real mass produced divided by the theoretical mass multiplied by 100. So when rearranging this, we need to do the percentage yield multiplied by the theoretical mass. So 13.5 kilograms multiplied by 92.3% is 12.4605 kilograms. Question 9 is about acids and alkalis. Dilute hydrochloric acid is a strong acid. Explain why an acid can be described as both strong and dilute. What makes an acid stronger is dependent on how much of the acid is ionized in water. So if an acid is fully ionized in water, it would be very strong. And with concentration, it's just how much acid is present in a unit's volume. So for example, you can have a small amount of hydrochloric acid in a large amount of water, and it would be dilute, but it would still be a strong acid inside the water. Or you can have a lot of hydrochloric acid and not much water added to it, and then that would be a strong acid, and it's concentrated because with the total volume of solution, most of it is the acid and not the water. So you need to think about how much does it ionize in the solution and how much of the acid is present in the whole solution itself. 9.2. A 1 times 10 to the minus 3 mole per decimeter cubed solution of hydrochloric acid has a pH of 3. What is the pH of a solution of hydrochloric acid that's 1 times 10 to the minus 5 moles per decimeter cubed? Well, 1 times 10 to the minus 3 is 0.001, and that has 3 zeros, and that's why that is a pH of 3, because it's times 10 to the minus 3. In the same way, to the minus 5 would have 5 zeros before the 1, and so it would have a pH of 5. 9.3. A student titrated 25 centimeter cubed proportions of dilute sulfuric acid with 0.105 mole per decimeter cubed sodium hydroxide solution. Calculate the concentration of sulfuric acid in moles per decimeter cubed. Use only the student's concordant results. Concordant results are those within 0.10 centimeters cubed of each other. Looking at the table, the only results in such way are titrations 3, 4, and 5. So we're just going to add those together and divide by 3 to get a mean value of 22.13 recurring. Now, what I like to do is to make a table and fill in what I know. So we know the volume of sodium hydroxide is 22.13 recurring centimeters cubed. We also know the concentration is 0.105. On the other hand, we know that the sulfuric acid has a volume of 25 centimeters cubed. Firstly, I would convert both the volumes into decimeters cubed because that's the unit we want the answer in. So I'm going to divide 1000 by both of those numbers and rewrite them. Next, I'm going to use the formula number of moles is equal to volume multiplied by concentration to find the number of moles of sodium hydroxide. So I'm just going to multiply the two numbers on the table to get 0.002324 moles of sodium hydroxide. And looking at the equation, we can see that 2 lots of sodium hydroxide is reacted with only 1 of the dilute sulfuric acid. Therefore, with this number, we need to divide by 2 to make them equal. And now we can find the concentration by simply dividing those two numbers together. So the concentration is the number of moles divided by the volume, which will give us an answer of 0.04648 moles per decimeter cubed. 9.4. Explain why the student should use a pipette to measure the dilute sulfuric acid and a burette to measure the sodium hydroxide solution. If you remember back to the titration practical, we need to measure a fixed volume of sodium hydroxide accurately 5 or 6 times. And pipettes are a great way to do this because they measure a fixed volume very accurately in each test. And a burette allows you to measure variable volumes accurately. So we can measure the amount of sulfuric acid needed to neutralize the sodium hydroxide very accurately. We can even use the burette to only allow drops of sulfuric acid to go into the sodium hydroxide solution. 9.5. Calculate the mass of sodium hydroxide in 30 centimeters cubed of a 0.105 mole per decimeter cubed solution. The relative formula mass of sodium hydroxide is 40. Again, I would write out my formulas that I may need. So mass is equal to moles multiplied by mR, or relative atomic mass, and moles is also equal to volume multiplied by concentration. Instantly, I would convert 30 centimeters cubed into decimeters cubed to make the equation work. So 30 centimeters cubed is 0.03 decimeters cubed. You need to divide by 1000. So now that we have a correct volume and a concentration, we can multiply those two numbers to get a number for the moles. So 0.03 multiplied by 0.105 is 0.00315. Now that we have the moles, we can also work out the mass because we have the relative atomic mass given as 40. To get the mass, we need to multiply the moles by the mR. So just multiply those two numbers to get a final mass of 0.126 grams. Well, that's 2018's paper 1 completed. In the next video, we will look at 2018's paper 2.